Hello. I know you might find this hard to believe, but I really miss you and I wish you guys were all here. But this is our first online chemistry lesson and I'm going to be covering 10.1. But first, I need to let you know that I want you to reach out to me if you have any questions as in what you're supposed to be doing, or if you have a prayer request or anything that you want to share with me, please email me. Y'all are going to laugh. But it's a little corny, but right here, S. Dixon, that's Dixon, at evajax.com. I would love to hear from you, and I'll be talking to you more about that in the future. But for now, let's go ahead and start with 10.1. This content is about the physical behavior of matter, and after you watch this video, you need to answer the questions on the Google form that I'm sending you the link for. So I think you'll find it pretty easy to do. And again, if you run into any difficulty or have any questions, please let me know. It's also really important to provide me with your first and last name, because especially if you have some kind of weird email address that doesn't have your name in it at all, I will not know who you are. So make sure you identify yourself, and also make sure you meet the deadline. We have deadlines for a reason, because you need to be consistently doing work every day, and make sure that you don't fall behind and end up getting zeros, because this assignment will be graded as an assignment grade in the grade book. So pay attention, keep up with all your deadlines, and I think it'll be a good thing overall. So, physical behavior of matter. You've been learning your whole life in different science classes about the 4 basic states of matter. Now, we have found some more states of matter that we're not going to be covering in this section, but those are generally created in a lab type situation and not common. And so we're going to stick with our 4 common states that we would see. Okay, and you already know this, but it's solid. So I have some little cubes here to represent solids. And then we have liquids. I have some cooking oil. We're not going to say the expiration date on this cooking oil because it might be a little scary, but this is our example of a liquid. And then this is the least exciting one, but the air in this beaker is our gas. And then probably the most exciting one is plasma. So you can see the plasma ball. Oh yeah, that's showing up really nicely. So we'll get to talking about each of those more in depth in just a little bit. But first, before we knew a whole lot about solids, liquids, gases, and plasma, there was a guy that came along named Robert Brown. And Robert Brown is not even a chemist. He is actually a botanist, or was a botanist. I've got a little thing for this. Y'all don't laugh, okay? I know you're probably laughing at me. Okay, but in 1827, that's almost 200 years ago, he decided that he wanted to study pollen. And you know what pollen is? It's the grains produced by a flower, and it's part of the reproductive cycle of a flower. And he wanted to look at pollen under a microscope. And every time he put the pollen on a slide and tried to put it under the microscope, it would like blow away. And if he tried to flatten it with a cover slip, it was just smushed and he couldn't get a good picture of it under a microscope. So he thought, you know what, I'll just suspend some pollen in water and then it'll be like 3D and it could turn around in the water. And he thought, oh, I could see it really well. And so that's what he did. He took just water, put some pollen grains in it, put the cover slip on, put it under the microscope, and he could see it pretty well, but the big problem that he had was it wouldn't be still. And so he was a little frustrated because he was just wanting to look at the pollen and get a good feel for it microscopically, and it would not stay still for him to look at it. And so then he realized that it wasn't the pollen necessarily, but everything actually moves on the microscopic level. So he and other scientists started looking at other things under microscopes, and nothing would actually be still. And so that led to the concept of Brownian motion. And so Brownian motion is the constant random movement of tiny chunks of matter. And they noticed this in just like dirt in water and other debris in water. Nothing seems to stay still. And so that concept of Brownian motion led them to develop what we call the kinetic theory. And so the kinetic theory, again, don't laugh. The kinetic theory is the fact that subatomic particles of all matter are in constant random motion. I'm sorry, it's backwards for me on this screen, so I'm gonna have to get used to that. Okay, but basically it's the idea that whether something is a solid, liquid, gas, or even plasma, the tiny particles that make it up, whether they are individual atoms or they are molecules, those are moving all the time. Okay, so let's start talking about how this would work in each of the 4 common phases of matter. See, I printed out my notes. Aren't you glad not to be writing slides right now? I know you are. So let's talk about solids. Okay, solids have definite shape and definite volume. I'm just going to go down to this copper one. And it's got copper atoms in a very orderly pattern, and they're kind of locked in place. But because of the kinetic theory, we know that they vibrate in their fixed positions. And so the particles, even though it's a solid and it's pretty consistent, they're not going to come out of their shape or anything unless they get heated up too much. And so, yes, the particles of matter in a solid are moving, but they're locked into their shape or their place by chemical bonds. Like this is copper, so it's a metallic bond, but if you had something else that wasn't a metal, like a piece of paper or a beaker with glass, I was using this to represent the gas inside, but the beaker itself is a solid. Okay, these particles are locked in and they can vibrate back and forth, but as long as they don't get too much energy, they're not going to come out of their ordered arrangement, and so they remain with a definite shape and definite volume. Okay, and then if you heated this up enough though, you could get this to melt. Okay, we've all seen people blowing glass, and we know that it takes a lot more energy, but all the metals that we know of will melt and come out of their ordered arrangement. And so when something melts, it's actually because it received enough energy for the particles to come out of their bonds and start moving around. And that's what happens in a liquid. Okay, this is vegetable oil, which happens to be a liquid at room temperature, and its particles are able to move all around within the liquid. They still have some attraction for each other, so they're not just going to go floating off into space or into the air. They're going to stay as part of this liquid. Can liquids evaporate? Absolutely. Okay, if they get enough energy, their particles can escape and go into the atmosphere and become gas-like. And so liquid particles are constantly moving. One way that we could illustrate this is if I filled this up with water and I put something like food coloring in there. Okay, the food coloring would disperse itself without me even having to stir it, because the particles of water are constantly moving around. Okay, so that's a liquid. And then I'll use this to represent the gas. Gas particles are really cool because they are definitely in constant random motion. They typically have way more energy than a solid, definitely more energy typically than a liquid. And they're gonna bounce all around. They're going to hit each other. They're going to hit the walls of their container. This is an open container, so air is constantly coming in and out. But if I were to put a lid on this tightly and be able to close it up, okay, the air would stay inside and just kind of keep hitting the other particles of air and the walls of the container. Okay, and so we can measure what we call pressure. Okay, pressure is the force acting on a unit surface area. And so we can do different things to change gas pressure, which we'll talk about in a later chapter. Okay, but I also want to talk about the fact that we consider gases at room temperature and at most normal temperatures to be ideal gases. An ideal gas is not a perfect gas. What that means is that as the particles are hitting each other, they don't attract each other, so they're not wanting to stick together, they're wanting to bounce off. And also we say in an ideal gas that the particles do not lose any energy when they bump into each other. Okay, so they're constantly bumping into each other, they're bumping against the walls of their container, and they're not losing energy. Okay, but retaining that original amount of energy that they had. In real life, they lose a teeny tiny bit of energy, but it's negligible, so we just call them ideal gases. When would gases not act like ideal gases? There are 2 circumstances. One of them is if you put the gas under really high pressure. That would mean that the gas was very much compressed and the particles are so close together that they actually do start interacting with each other more. And so the first situation where a gas would not act like an ideal gas if it's under a lot of pressure and really squeezed in tightly. And so imagine if I took a bunch of air and I made it into a super tiny space, then the particles of air would start interacting with one another. The other condition in which a gas would not act like an ideal gas is if it's really, really cold. Because if you'll remember from past discussions of the kinetic theory, the warmer something is, the faster it's going to move around. The cooler something is, like the less energy it has, the slower the particles would move. And so it is possible to have a gas that's really cold and the particles are just moving so slowly that they have more time to actually interact with one another, and then they would start behaving differently than an ideal gas would behave. And so we've covered solids with the particles very nice and tight in an orderly fashion, stuck together, locked into their fixed positions, even though they're vibrating around in their fixed positions. We have liquids where the particles are free to move around, but yet they're still attracted to each other. And we have gases, just imagine the air in here, where the particles are definitely free to move around. The volume can change, especially if you have a container with expandable sides, like a balloon or a hot water bottle, something like that. And then the final one that we're going to talk about today is plasma. This is probably the one that you know the least about. It exists on Earth naturally in lightning for a few brief seconds. The sun is actually plasma. Stars are plasma. Remember, stars, including our sun, are not burning. There's no oxygen in the air. It's a series of nuclear reactions that are very hot. And that's what it takes for plasma is either really, really high heat or electricity. Like there are gases within this plasma ball that as soon as electricity hits it, it causes them to separate out between electrons and positive nuclei. And so you have a bunch of positive and negative charges going around, and these charges are attracted to the electrical impulses in my hands. So that's kind of cool. And we see plasma also in fluorescent lights. I mentioned lightning already. For that brief second that lightning is happening, that is plasma in the air. And of course, the stars in the sun. And plasma is really high temperature and really high energy. And that's why it's important to have like protective coverings over fluorescent lights. This is in a protective glass. Okay, if it breaks though, it will cool very quickly because it's exposed to the air and immediately would start to cool down. So we still want to stay protected though when we're dealing with plasma. So we've covered quite a bit, and I really just did like the first part of section 10.1. You should have defined the vocabulary terms yesterday and turned those in already online by emailing me. And hopefully everybody got that done. If you didn't get it done, it's due by midnight on Tuesday, which you should be watching this video on Tuesday probably. So keep all of your dates in mind. And again, I cannot emphasize this enough. I do want to hear from you if you have any questions or if you have a prayer request that you would like me to pray for you about. Let me know, because I'd love to hear from you, and let me know if you're having any issues whatsoever. And you'll see me again soon, hopefully, on the next video.